My name is Arden Scortis, and today I'm going to be going over my Physics 2212 Lab 3 on circuits. For introduction and purpose, we are going to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in parallel, use the multimeters to measure values of conventional current and potential differences in the circuits, examine the behavior of ohmic resistors and capacitors. So to go over some key fundamental physics concepts that we will cover in this lab, first we use Kirchhoff's circuit laws, which includes the node rule. The sum of currents flowing into that node is equal to the sum of currents flowing out of the node. Next, the loop rule, which is the sum of all electric potential differences around the loop is zero. Ohm's law, which is volts equals current times resistance, and the equation for capacitance, along with conservation of energy and charge, time dependence in RC circuits, steady-state circuits, resistors and capacitors in series and parallel. So for experiment setup, use online model of a circuit to observe the behaviors of different combinations of resistors and capacitors and compare and contrast the data of different circuit models. So for a preview of the results, the system is the circuit and everything else is its surrounding. The initial conditions are two 1.5 volt batteries, 2 ammeters, and 2 resistors of 47 ohms and 100 ohms. Current and voltage values given by the model match predictive values. In an RC circuit, magnitude of the current is time dependent. For part 1 of this experiment, we first had to predict the current flowing through a circuit using the loop rule. My prediction was that the current would equal 0.02 amp. My voltmeter readings were 3.0 volts and the current 0 amps because it was an open circuit. For part 2 series circuit, the ammeter reading doesn't change because the voltmeter has a very high resistance, meaning that no current flows through it and the path of current remains unchanged. This satisfies the loop rule and the current is equal to 0.02 amps. Here is a graph of the potential difference versus the position around the circuit. The batteries raise the potential and the wires have negligible effect on the potential. The resistors in the circuit lower the potential by having negative potential differences. You can see that the battery went up to 3 volts, then across the resistors, and then down to 0 volts. You can see the steeper drop-off is around the resistor that was 100 ohms. Here in the lab, we examine when you attach a voltmeter, why doesn't the ammeter reading change? When you do this, when you touch the voltmeter, it has very high resistance, so very little current flows through it. So the ammeter doesn't really change since the voltmeter doesn't affect the current in the rest of the circuit. When the parallel ammeter circuit is created, the current splits into two paths since the ammeter has zero resistance. All the current goes through it and creates a higher current rating of 0.06 amps. Here in part 3, we have an RC circuit connected to two different bulbs, a 10 ohm bulb and a 20 ohm bulb in a capacitor series. The bulb lights up and then slowly starts going out, and the current decreases from maximum to 0. Then we disconnected the battery and the bulb lights up again and then goes out. In this experiment, like I said, we had to record it with a 10 ohm bulb and a 20 ohm bulb. And here at the bottom of the screen, you can see the times it took to charge and discharge for each of the 10 ohm and 20 ohm bulb. Here we have time-dependent voltage across a discharging capacitor. This RC circuit, we had a 9-volt battery, a 200 microfarad capacitor, and a 30 ohm light bulb. First, I had to measure the voltage across the capacitor discharging, then record voltage and time, and plot data. I then calculated the line of best fit and time constant, which was 5.998 versus the expected, which was 6. I did this by using the two equations on the left. Next, for possible sources of error in this experiment. Since a circuit model is used, it is highly unlikely that the data is incorrect. However, the main source of error in this experiment is most likely to come from human error for inaccurately recording the voltage and times for charging and discharging using the stopwatch, which would have led me to get incorrect data points. Next, to answer a few questions about this lab. For the first question, if an actual ammeter would have been used, it would have had some resistance instead of zero resistance, such as in our ideal circuit model. Overall, the current would have decreased due to experiencing the resistance of the ammeter. For the second question, if there was no resistor in the circuit, that means that the circuit model would have reached full charge immediately, since there isn't a resistor to slow down the current. In real life, this prediction would not happen because wires have some resistance. This means that the capacitor will likely be charging at a slow rate. Next, for some conclusions of the lab, the node and loop rules are important tools in observing and calculating different properties of a circuit. Currents and voltage are time dependent and decrease exponentially with time. And to calculate accurate values for an ideal circuit, wires and ammeters must have zero resistance. Thanks for listening.